So we are starting the session again. My screen. Oh yes, I have shared the screen. So the next session, now in this session, we learn about the test of association. That is the chi-square test and correlation for the qualitative variable, which we have learned. And again, qualitative, I think by this time you know that qualitative has got two categories, that is the nominal and ordinal, and interval and ratio comes as a scale variable. So for scale variable, we use correlation. Yes, ordered and unordered, Ankita is right. And for qualitative variable, which is the ordered and unordered or nominal and ordinal, we use chi-square test of association. So coming to this session, so first we learn the basic concepts of chi-square, what are the research questions, and till now we have learned the descriptive statistics. So descriptive is only describing about the data, but in analytical you infer about the population. So it's an inferential statistics. So now from now onwards, you will see that there are two hypotheses, null hypothesis and alternate hypothesis. In descriptive, we don't have any hypothesis. It's only the uh, summarization of the data. So here we'll see that the basic concepts, then the research question, assumptions and hypothesis, what are the commands and interpretation, and overall summary. So if you see the research question, a typical research question can begin with the, is there any association between gender and diabetes status? So I just want to know whether the diabetes is like, has it got any association with male or female or vice versa? So I conducted a study where I have selected the subjects and I have asked two questions from each of them. What is your gender? And are you a diabetic? Yes or no? And then I collected the data and I made the contingency table. So what do I mean by contingency table? So basically a contingency table, it is also known as the cross table or cross tab or two-way table. And it is an arrangement in which the data is classified according to two categorical variables. Like age, in this case, gender and the diabetes. Both are the categorical variable. Gender as male and female and diabetes as yes and no. So these both are the categorical variable. So we will make a 2 by 2 table. So this is a 2 by 2 contingency table. Male and female as a row and diabetes and no diabetes as a column. And generally you see in chi-square, we put the dependent variable in column. So remember DC. We remember in our 10th, we used to learn the DC and AC current. So you can remember this by DC. D is for the dependent variable, C is for the column. So generally we move the dependent variable into the column. So here the diabetes is the dependent variable, the status, and the gender is a independent variable. So we have 2 by 2 contingency table. We can have a 3 by 2 contingency table where we are seeing the association between the three categories of BMI, and the three categories of BMI are normal, overweight, and obese. And the two categories of diabetes are the presence of diabetes or absence of diabetes. And this is the 3 by 2 contingency table. So you may get a result like this after you have tabulated it. So just see these table for a few seconds. You can see here, see the first table. So first focus on the first table. Here you can see that the male and the female in diabetic and non-diabetic equal number. In the second table, you can see that diabetic male is 45, non-diabetic 35. Similarly, the females are 20 and 30. See the third table. Here the diabetic male, they are 60, non-diabetic as 20, and females as 10 and non-diabetic as 40. So if I don't have any statistical test or I want to have some inference without using any statistical test, can I say something regarding no association, some association, and strong association? So Shantanu has written 1 is no, 2 is some, and 3 is strong. Okay, perfect. So, right. So I have taken your answer, Shantanu. Varalakshmi is also written correctly, that no association, some association, and strong association. So just even without applying any statistical test, just by seeing the numbers in the cells which seem to be unbalanced or unequal, you can infer to some extent that whether it is a strong association or a true association, or there's no association. So what are the various research questions for which we need this chi-square test of association? So the first research question, if we want to learn or to estimate the relationship between the various categories of BMI and history of cardiovascular disease, just like we have seen the example of diabetes. Instead of diabetes, we have taken the cardiovascular disease, whether it is present or absent. The second research question can be association between the surgical technique X and surgical technique Y. So there are two surgical technique X and Y, and you want to see whether the surgical site infection has got any relationship or the association between these two techniques. The third research question can be association between the quality of sleep, which is good versus poor, and academic performance, which is again, you have classified it as good versus poor for medical undergraduates. So in all these three questions, what have you seen? That all these are qualitative variable or the nominal and ordinal variable. So in all these, what we have observed, that there are two categorical variables in all the questions, and we are trying to look for any association between them. So what is the appropriate statistical test? So appropriate statistical test is a chi-square test of association or chi-square test of independence. We also call as a chi-square test of independence because we assume that they are independent to each other. That means there is no association. So it's just the way of saying it. So both are correct. Chi-square test of association or chi-square test of independence. But again, this association does not indicate causality, because for causality, there are other criteria also which needs to be fulfilled. Here, you are only conveying that yes, there is some association, and then for causality, you can apply other statistical tests and other criteria. So now, since you know that this is an inferential statistics and we know that it is a data set is there, but we, in all these hypothesis testing analysis or the inferential statistics, we always see the suitability of the data to apply that particular test. Because a computer is not a, you can say it is only dependent on the command. So it is we who will give an appropriate command to the computer to perform a particular statistical test. So that processing should be there in our mind. Otherwise, if you click, something will come automatically. We have seen many people applying and using many statistical tests like ANOVA. Of late, I have seen a repeated measure ANOVA. A person from a microbiology department on a data set applied ANOVA, clicked on the graph also, something will come definitely. But then you cannot interpret, because ultimately whatever is coming, you need to make an intuitive meaning of that particular output. So that's why I always say that you need to understand that what assumptions and are they met or not, and if the assumptions are not met, what implications it can have in your analysis or output, or how can you modify your choice of the test depending on the assumptions. So if you go for this chi-square test of association, then the first assumption is that both the two variables should be categorical in nature. That should be satisfied. Second is it should be, all these categories should be at least two and more category for each variable. And the third is like there should be independence of observation. So now what is independence of observation? This is one assumption which states that if you have counted one individual in one group, you will not count that individual in the other group. For example, if there is one person, I have taken him as my study subject and I have classified him as obese. Yes. So obese, if I have classified him as obese, I cannot put the same person in non-obese. So I will count that person in under one column in having that one particular nature of variable. And then it should at least have a relatively large sample size. Because there are certain corrections. We will see that like there is a Yates continuity correction and there is a Fisher exact test. So all those corrections you need to apply if there are small sample size. So one assumption is like it should have a relatively large sample size. So large sample size is generally like you can say there's no definite this thing, but we can say like at least more than 40 or more than 50. So because for Yates correction, we say that if the sample size is less than 40, and then you see the individual cells also about the expected and observed frequency. In that case, you may need to go for those corrections. So relatively large sample size is required. That's why we emphasize on the calculation of the adequate sample. So somebody has asked regarding two or more categories for each variable. Yes, any example means generally whatever categories we select that should have it. You cannot have only single category. That is understood because then in 2 by 2 contingency table, the other it will not be populated. So like two or more categories means like let's say the diabetes and the gender. So both has two categories, or obesity versus cardiovascular disease. Obesity, if you are taking the BMI into three category, so three categories versus two categories. So depending on the contingency table, 2 by 2 or 3 by 2 or such type of contingency table. So independence of observation, there's one more thing to understand in the independence of observation, that there should not be relationship between the subject in two groups. That means like if I'm studying the gender and diabetes, then I should not take like 40 spouse. I may keep 40 female in one group and 40 male in other group as male and female, and then I may ask as a diabetes yes or no, but that will violate the assumption of independence of observation, because husband and wife, they are somehow related to each other. They have got some relationships, so that lifestyle, many of the factors are interrelated. So there will be a lot of confounders. So that's why we say that there should not be relationship between the subjects in each group. And this is also one of the things which we should consider while saying this independence of observation. That means that the observations are paired somehow. And the relatively large sample size, what do we mean by that? That means that expected frequencies. Mind it, this is the expected frequencies. This is not the observed frequency. In the 2 by 2 table, the frequency which you see, that is the observed one. But there is something known as the expected frequency. Why? How do we count the expected frequency? We'll see that there's an option. You can click that and you can see the expected frequency. But expected frequencies should be at least 5 for majority of the cells. It should not be less than 5. So the null hypothesis is that there is no relationship between the variables, and the alternate hypothesis states that there is association or relationship between the variables. So expected frequency is, again, it is defined as count in each cell if the null hypothesis is true. So we see that there is no association between these two. So if the two variables are independent of each other, then the observed count will be equal to the expected count if there is no relationship between these two. If it is not so, then definitely both these will differ. Observed count will not be equal to the expected count. Now there is something known as the strength of association. So, or the effect size. So we will learn again. Okay, so you want to this expected frequency, okay? So expected frequency generally is calculated based on the null hypothesis. what is a null hypothesis? Null hypothesis states that there is no relationship between the gender. That means the overall which you see, we'll see that in table also. But whatever is the overall presence or absence of diabetes, gender has got no role. That means same proportion you will see in case of each cell also. So you consider expected frequency, that if the two variables are not related to each other, then what is the expected count? That means there is no association. So this expected frequency is calculated based on this assumption that there is no association between the two. And then you see the actual one, that means the observed count. And I'm not going into the statistical definition, like basically you calculate based on the difference between observed minus expected, and then you sum it up and then divide it by expected. But I'm not going into that formula, since in Jamovi or in any statistical software, you get that value from the software. We only need to interpret it. So we'll see that more in the 2 by 2 table, how that expected is calculated. Uh, there is something known as, like, that row into column divided by sum total. That is different, but I'm not going into that statistical thing. I'm only telling you how to interpret it. So I'll again tell this once we see the 2 by 2 table. Yes, you are right. Row total into column total by grand total. But this is the statistical thing, which I don't want you people to know, because I know that you have already read this. For me, it's more of a concern that you should understand the interpretation, and you should be able to give your uh, piece of brain, like what do you think from that particular output. So, and in that context, there is a importance of a effect size or the strength of association. But this effect size or strength of association, this we apply only when the chi-square value is significant. If the chi-square value, like p value, is not significant, then there is no need or there is no intuitive meaning for this strength of association. And for chi-square, there are various measures for expressing this strength of association or effect size. Like, that there is a Cohen D, and there is a Hedgehog G, and there is a other, like, phi coefficient is there. In ANOVA, you will also see that there are other coefficients. But in case of a chi-square, generally we use phi and Kramer V. Uh, Generally we use Kramer V. Why? Because phi is only there for 2 by 2 table. And Kramer V is there for 2 by 2 or more than n by n contingency table. So what is the interpretation? If the value is up till 1.1, we say that it is a small effect size. If it is up till 0.3, we say that it is a moderate effect size. And if it is up till 0.5, we say that this is a large effect size. So this was regarding test of association. So I'll just show this in the Jamovi, how to do this. So let's see the question. So if I go into this is the question. So the question is like, I have done a retrospective study of 180 hospital record of COVID cases, and I want to know what factors were associated with the oxygen requirement in COVID cases at the time of admission. And I have to see, like, association of oxygen requirement with smoking status of patient, and association with oxygen requirement with disease severity of the patient. Okay, so these two associations I have to check whether the oxygen requirement is more in case of a smoker or non-smoker or something like that. And again, the disease severity. So this is my sheet, and and we have shared this with you also. So I think let's start from the beginning. I'll delete all these analysis. So you can remove, if you click on select and remove, all these analysis will be removed. I don't know how many analysis it is there. So I think all these previous they are saved. That's okay. All remove. So I've removed all the analysis. Now this is the data set. First, I'll explain you the variables. These are the variables: serial number, name, resident status, then hospital type, and then you can see gender. You can click and see like type A, type B hospital. Similarly, you can keep on scrolling. This gender is same as what we have seen. Then there is a age. Then this age group I have created. And then this is the socioeconomic status. So similarly, you will see that smoker and non-smoker and other uh, variables are there. So I'll go to this analysis. In analysis, I will use this option of frequencies, this one. This option. So you can go to this frequency. You can see there are various options. One sample proportion test and contingency table. So right now we are focusing on this option. Contingency table, where it is the chi-square test of association. Independent sample, because these are the independent samples and we are using the option of chi-square test of association. So I will click on this frequency, independent sample. If you open this, you can see there is a row and there is a column. So my first question is what? I have to see the, so document. So we have shared the data set with them. We have shared the data set with you people. Should we share it again? Can you please?
Shared, ma'am.
Shared, okay. Shared, so you can check. Doctor, I think who has texted this? I'll written in the chat. You can again see.
That's in session 2, that's why. Maybe checking session 1.
Okay. Okay. So you can check that particular session. We have shared with the name of session only, I guess. So the name of the file is demo test of association proportion risk estimation. Risk estimation, we are not telling this time, but the same data set we have used earlier. You can practice on your own also. So I'll go to this sheet. So there is a row and there is a column. So which one, if my question is to see the association between the smoking status and the oxygen requirement. So which is dependent and which is independent? Because accordingly, I'll transfer those variables. Because remember, we have talked DC. D is for the dependent and C is for the column. So in the column, I have to transfer the dependent variable. So I have to see the oxygen requirement. So oxygen requirement is my dependent, yes, and smoking is my independent. So this is the smoker. I'll shift it in row. And if I scroll it down, this is my oxygen requirement, oxygen 1. So I'll shift it in column. So this is my 2 by 2 table. And again, if you focus, you can see this is the sign of ordinal and the ordered and unordered. These are the two signs of the variables which you can enter here. So now, if you see the chi-square value, the chi-square value, what is the chi-square value? 0.04 p-value. Otherwise, the value of chi-square is 3.89. And this is the count. This is which count? Observed count or expected count? This is which count? So this is the observed count. This is not the expected count. Yes. So yes, few of you were asking regarding the expected. So if you see this proportion, so in overall, you can see that oxygen requirement is there in 132 and in 48. In 132, there is no requirement of oxygen, and in 48, there is a requirement of oxygen. So if you apply this same proportion here in no smoker and smoker, then it will be your expected count. Did you get it? If you
180, 132.
if you write like out of 180, there are 48 who require the this oxygen, right? Similarly, there are, if you apply the same proportion here in 123, so whatever number comes, that is your expected count. Null hypothesis means that gender has got no relationship. That means whatever is the overall proportion I am seeing it here, that will be there in the gender also. Okay. But here you don't have to calculate. If you see this, there is a option which is the expected count. If you click this expected count, you can see this is the expected count. So out of 122, no smoker, 32.5 is there in the yes, and 89.7 is where there is a no oxygen requirement. So it is the same which I have told you, the way you assume that this is the requirement. If you don't consider that gender has got no effect, then it will take the same proportion as this one. You can do that using unitary method. Like if there are 48 out of 180, so in 122, how many of them will be there? You can do it. It is the same way. And that's how that formula comes, like row total into column total divided by sum total. That is seeing that unitary method only. So the expected count, now you need to see. Okay, so once more. So once more, I was just telling you how you can calculate the expected, like how to understand what is expected count. So basically, there is a formula for expected count. I know that you know that it is row total into column total by sum total. But I was just telling you that you assume that the null hypothesis is, what is a null hypothesis? That there is no association between the smoking status and the oxygen requirement, right? So if you don't take this smoking status, forget this for now, and only take this observed one, which is the out of 180, there are 48 smokers. So if I use the unitary, if I am calculating it for the oxygen requirement. So if in 180, all of you do, if in 180 there are 48 smokers, how many smokers?
48 smoker now.
Oh, sorry, 48 who require out of 180 smokers. If there are out of total 180, if there are 48 people who is requiring oxygen, right? So if there are 122 no smoker, and if you apply the same proportion here, how many of them will be there? So in one, it will be 48 by 180. And in 122, it will be 48 by 180 into 122. So I'll show you here in the calculator. So if you open this calculator, let me minimize this. Why I have. Yes. So I will do like 48 divided by 180 is equal to multiplied by
Oh, it's coming.
Am I audible now? Yeah, Bharat, you are right. There were some technical issue, but I think I'm done now. So I'll show you again. So just for